Hello everyone. So right now we are back with the next video, which would be for the second problem of the set, that is given the root of a binary search tree T having integers as the information part and two integers k1 and k2 as the input. Write a function to get all the elements in the range from k1 to k2 in the search tree. So how do we approach this? Basically, we need to store those values somewhere, right? So that's where our implementation uses this idea of basically storing them and printing it out. But basically, we could do something more. We could do a recursive call, okay? And in that recursive call, we do the printing in this particular manner. Basically, we don't need to store. We basically just check if it is greater than or less than, and we do it. So let's approach it aggressively. Now, oh, by the way, I do have the documentation written here in details for this one. This is the particular documentation. If you want to, you can read the logic behind this, but we of course are going to go to the code and explain the logic. So what happens, you just put the root in the function, and along with that you ask the user to input the ranges, that is k1 and k2. Of course, if basically you are if there is nothing, you are beginning at the unit, you are at the beginning, so you just return, you go back, and that's it. You don't do anything. Now, if the data is greater than k1, then recursively call for the left subtree, because if you just go and check the tree structure, you do know that from the root, you on the left, you basically have the node with the data value less than the root node, and on the right you have the data value which is greater than the root. Now this goes and goes and goes continuously to create the binary search tree. See the first video for that. Now, if the root data is actually greater than the k1, that's your minimum range limit. So suppose it is 0 to 100, or maybe 10 to 50, or whatever be it, then the 10 we are talking about, or the 0 we are talking about. Here, basically we are calling the left node of the root. So from here, 25, so it's 20. Suppose the range is, let's say, 10. So if it is greater than the value 20 is greater than 10, then of course we are going to go into the root left, means we are going to go into the left subtree and basically recursively call it. As we do the recursive call, you will see how it goes on. So of course the root is not equal to null in our case. So, and as you can see, if you just continue with it, we are going to we are just traversing till the path it is still in the range. That means it is greater than the minimum value, or not minimum value, the k1. Okay, if the roots data is within the range k1 and k2, then we print it. Basically it has to be again checked for if it is also less than the maximum value that is given by the user. So the maximum value may be 40, 50, whatever be it, and it has to be less than that. So if both of these conditions in this if statement are true, suppose you go to this print range, okay, and you go and you find till, let's say, 10. If it's at 10, then the less than or equal to condition suffices this part with sorry, yeah, oh, I forgot to wait, let me just check the question real quick. Range from k1 to k2. So maybe we can actually do this. We can have this as greater than or equal to, which would probably be better, I think. Yeah. So if that's the case, then no, if that is the case, then we probably will not be stopping here. So then we'll be going here, which is a redundant case. So that redundancy we need to what do you call this, not do that redundant case. So we are going to stop at this path only, and then only we are going to check, okay, yeah, if it is greater than k1 or if it is less than the k2, then we print it. Okay, and then if we find that the roots data is actually smaller than k2, then we recursively go into the right subtree. Okay, basically we are doing the other checking where we go lesser than the maximum value, and with that this whole function basically prints the data, but it never stores it. There are other applications like implementations where you basically have a stack or a queue which continuously does the checking and then stores it into the puts it in the stack or the queue. but the question just only wanted us to print it, right? Write a function to get all the elements. So probably get all the elements never specifies that do we need to store them or not, but this particular function just prints them. Or if you just see that, okay, so suppose I also want to store it, then just create an array somewhere. Okay, maybe in this function or maybe here, depends, because in C you only can return one particular output of the function. So you also need to add the storing queue or the storing stack, and then you just do the enqueue or push operation with here. Okay, with that being said, as you can see the documentation as it loads, yeah, basically you have a BST. You then do the logic behind is basically if the root is null, then do nothing and return. Check the left side of the left subtree, and if the current root data is greater than the k1, it's possible that the nodes in the left subtree could be within the range this possible. So that's why we recursively call the print range, and then we basically go and check if the root data is less than the k1, which if it is, then it is not our case. Okay, then the entire left subtree must also be less than k1, so we don't need to explore it, of course. That's what I just said. And yeah, basically you just check if the current root data value is within this range by checking the right subtree if it is less than the k2, less than or equal to the k2, and then basically we print it. And that's the logic. That's the logic. Very simple, right? Now if that is done, we can actually show the application of this by just running it. So currently the program is running, so just give me a second. Okay, somehow I'm having some issues. Why the terminal is not loading up, I have no idea. I forgot that there should have been an option to call out the terminal here. Why was the terminal not loading up with the shortcut? No idea. Whatever. So we will just go and do let's run our tree program, and we just going to create a, what was that? Okay, what just happened? That was a very weird glitch. So semester, let's go. Okay, we can just run it here. Let me increase the font size a bit. Oh, because I'm already inside the program, I can, let me increase the font. Oh, is it because now I know what was the issue. Okay, whatever. So let's go and do it. So let's just run the tree program, and here what do we need? We first create a random tree. So yeah, wait, what was it? Okay, oh, my function log. Okay, my function log was on, that's why I was thinking about this. So because of that, now okay, now suppose I want to enter something like 10, or not 10, let's do it 15. Yeah, so now we have a good tree. Let's just go with our practice set 2, so that is 6. Now first, this is not a binary search tree, we need to convert it to a binary search tree. For that we are going to go for the problem number 7. Of course in the later video you are going to understand how it works, but yeah, this is the tree display, basically how it was. Now after applying the binary like conversion, you basically have left side is 20, right side is 112. Here left side is 10, which is less than 20, and right side is 38, which is greater than 20. And this logic is followed to true and true to be able to just have this kind of display. So after that we go to the 6th problem again, and as we go to the 6th problem, we are going to apply the first whether it is a binary tree. We just check it. Yeah, it is a binary tree. Very good. Now after that we just do the we do the 6th option, which is basically check if within the range. So we do the second option and start range. Okay, so range, we can go from 10 to, let's say, 70. What do you think? We do the 10 to 70. So enter the starting range, which is 10. So we enter 10. Then suppose we do the 70 right here, 70. And then these are the nodes which lie in the range. As you can see, you can check it with this tree. And yeah, we are done. So that's it for now. Oh, this thing, there is this function locator. So yeah, goodbye, and let's meet at the problem number 3.